Have you ever played bumper cars? Does one even play bumper cars? I don't really know what you do, but you do the bumper car thing. Have you done that? Well, in bumper cars, you run into each other as fast as possible, and that causes the other bumper car to bounce back. And you know that the faster you're going, the harder that hit is going to count. Here's the thing though, this collision is elastic because of the bouncing. It's the bumpers on the car that make this a mostly elastic collision. And we can use the masses of the cars and their initial velocities to actually figure out how fast they'll be moving after the collision. So in this video, we're going to look at elastic collisions and actually calculate velocities before and after things collide. Let's take a look. Let's begin by taking a look at our lesson objectives. What are we going to get done during this lesson? First, we'll review elastic collisions. Those are the collisions where things bounce. Then we'll develop the equation for elastic collisions. So when two things collide, we can actually figure out, say, the velocity before and after these collisions. And we really will develop this. We'll take our time so that you can see where each of the little variables in this equation comes from. Then we'll use that equation to solve elastic collision problems. All right, first up, let's review elastic collisions. Remember that elastic collisions are a collision between two objects where things bounce. So we want to ask, did the objects bounce? If the answer is yes, like say a racquetball, then we have an elastic collision. Also remember that we went over several important facts for our elastic collisions. First up, we said that kinetic energy is conserved. That means the energy that comes from motion before and after is the same. So you'll see motion before and after an elastic collision. Secondly, we said that shape is not permanently deformed. In other words, the shape can change a little. When the racquetball collides with the surface, it'll squeeze and compress a little bit, and then it's just going to bounce back to its normal shape. So it's not permanently deformed. It's just changed its shape for a second. It bounces. Thirdly, we said objects can end at different speeds, one moving faster, another slower. And lastly, we said that perfectly elastic collisions are rare. This is just kind of a caveat for you to know. It's not actually going to be that important when we solve problems. We're going to assume collisions are perfectly elastic and solve for our answers on that basis. Let's take a look at a problem we might solve using our elastic collision equation. Here we're told that a cue ball, which is, by the way, that white pool ball, is gently hit at 2.2 meters per second into a yellow ball initially at rest. After the collision, the cue ball continues to drift forward at a velocity of 0.3 meters per second. What is the final velocity of the yellow ball? Assume both pool balls have a mass of 0.140 kilograms. Basic situation, that white cue ball is going to be hit into that yellow ball that's not moving at first. Afterwards, they're both moving, but the white ball has slowed down. And what we want to figure out is how quickly is that yellow ball moving. Now, of course, over time, the yellow ball is going to slow down because of friction. We're just ignoring that. We want to know how quickly does it move right after that collision. And it all starts here with conservation of momentum, which tells us that P initial is equal to P final. What in the world is P? Well, remember that's our variable for momentum, which is equal to mass times velocity. So initial momentum is with the subscript I. So whenever you see a subscript that's a little letter in front of the big letter, in this video that's I, that means initial. That means before the collision happens. And the F, you can probably guess, means final momentum. That's the momentum after the collision. The interesting thing is, in a collision, we have two objects moving, the yellow ball and the white ball. And so that means our initial momentum can be broken down into two parts. So take a second, look at those variables and see if you can figure out what they are. It's okay if you can't, but it's a good exercise to try to get your head around where this came from. Well, that P sub y, comma I, that's a lot, is the initial momentum of the yellow ball. So basically we're just saying, hey, at the beginning, the yellow ball has some momentum. Turns out it's actually 0 because it's at rest, but we need to take into account both objects. And the next one is the initial momentum of the white ball. So we're just considering the momentum of each object separately, and we're saying, hey, when you add those two together, you get the total initial momentum, and that's what's going to stay the same during the collision, from initial momentum to final momentum. On the flip side, we can also write final momentum in terms of the two balls separately. Again, try to figure out what those variables represent before I tell you. Pause the video even, take a second, and see if you can figure out what each of those stand for. Well, as you may have guessed, this first term here is the final momentum of just the yellow ball. And the second term is the final momentum of the white ball. All right, so that's a lot of variables written on the screen, and I understand that can be overwhelming, but it's about to get worse before it gets better. Okay, the good news is I always will have this equation for you on your notes, and you can just look at that. So you don't need to memorize it or anything like that, but we are going to see where this comes from. Remember that momentum is equal to mass times velocity. So now we can substitute mass times velocity into each of those momentum terms. That means the mass of the yellow ball, that's what m sub y stands for, times the velocity of the yellow ball initially is going to be equal to that momentum of the yellow ball initially. So that's where those two terms came from. And then same with the white ball, we substituted in the mass of the white ball and the velocity of the white ball. So again, we're just building this equation slowly. Now, try to write the other half of that equation in terms of mass times velocity. So take a second and rewrite the momentum of the yellow ball and the momentum of the white ball in their final state, just like we have here on the left. Pause the video, give that a try. Here's what we should have gotten. That the mass of the yellow ball times the velocity of the yellow ball final, plus the mass of the white ball times the velocity of the white ball final is all equal to that final momentum on the right-hand side. Okay, and this equation, we've used subscripts that very specifically refer back to our problem, but in general, for any elastic collision, we can write this equation. The mass of the first thing times the velocity of the first thing initially, plus the mass of the second thing times the velocity of the second thing initially is equal to the mass times velocities after the collision. Okay, so this is your elastic collision equation that you can use for any elastic collision problem. Let's go ahead now and actually use this to solve our cue ball problem. Now, what steps should we follow here? Well, whenever we have a bunch of variables like this, it's always really good to start by identifying the variables. So just write down a list of all the variables in your equation and write down what you know. For example, we know the masses of all of those. We know some of their velocities. And then we're going to plug in those variables that we know. And lastly, solve for the unknown variable. All right, I think we're finally ready to try to solve this problem. Let's start by listing the variables that we know. We know the masses of the pool balls. For example, the mass of the yellow ball is equal to 0.14 kilograms. And that's actually exactly the same as the mass of the white ball, 0.14 kilograms. All right, then we know the velocity of the yellow ball. That's the one that's being hit. It starts at 0 meters per second, an impressive velocity. The velocity initial of the white ball is 2.2 meters per second. And then we know that we want to solve for the velocity final of the yellow ball. We don't know what that is, but we do know the velocity final of the white ball. And that is 0.3 meters per second. All right, so those are all the variables. And now we're ready to plug them into our big old long equation on the right. Let's do that. We're going to plug in the mass of the yellow ball first, which is 0.14. And we're going to be multiplying that by the velocity there of that yellow ball initially, which is 0. Then we'll add to that the mass of our white ball, 0.14, times the initial velocity of our white ball, 2.2 meters per second. That's all equal to the mass of our yellow ball, 0.14 again, times the velocity final of our yellow ball. That's actually what we want to find. So we'll leave that as a variable. Plus the mass of the white ball, which is, again, for the last time, 0.14, times the velocity there of the white ball finally, which is 0.3. So that's what it is at the end of the problem. All right, that's a lot. Let's start to simplify. Well, conveniently, this whole thing goes to 0 because it's multiplied by 0. And then 0.14 times 2.2 gives me 0.308. That's all equal to still my 0.14 times velocity y final plus 0.14 times 0.3. When we multiply those two things together, we get 0.042. All right, to simplify, we're going to subtract from both sides 0.042. And that's to get the Vy by itself. When we subtract those from both sides, we're going to get 0.266 equals 0.14 velocity y final. So we're almost there. Then we just divide both sides by the 0.14 to get velocity y final by itself. That's going to cancel out there, and we're going to get the velocity y final as 0.266 divided by 0.14. When we do that, we get 1.9 meters per second. And that's already rounded there to the correct number of sig figs, which is 2. So that should be our final answer. Let's practice using this elastic collision equation just one more time. This problem says two hard steel carts collide head-on and then ricochet, like bounce, off each other in opposite directions on a frictionless surface. Cart 1 has a mass of 0.350 kilograms and an initial velocity of 2.0 meters per second. Cart 2 has a mass of 0.5 kilograms and an initial velocity of minus 0.5 meters per second. After the collision, Cart 1 recoils with a velocity of minus 1.5 meters per second. What is the final velocity of Cart 2? All right, to start to get your head around a problem like this, let's draw a picture. So first up, we have two carts. One cart, let's say, is traveling to the right, and it's traveling to the right there at 2.0 meters per second. The other cart is traveling to the left, and it's traveling at 0.5 meters per second. We say it's negative because it's traveling in the opposite direction. So this is all before our collision. And then we have a collision, and afterwards, they're traveling in opposite directions. They've ricocheted off of each other. So cart 1 now is traveling back to the left, and we've indicated that with the negative sign of the velocity, and its velocity is 1.5 meters per second. Meanwhile, this other cart, cart 2, is now traveling to the right, and we don't know that velocity. So that's what we're looking for. Now, remember, when we use all the proper subscripts, this is going to be velocity final, comma 2 equals question mark. So we're going to be looking for the final velocity of that second object there. All right, let's clear our drawings and then start working on this algebraically. Now that we're ready to solve this problem algebraically, I've put our equation on the screen for our elastic collisions, and let's start by just listing the variables we know. First, let's list information about cart 1. We know the mass of cart 1 is 0.35 kilograms. We know that the velocity of cart 1 initially is 2.0 meters per second. Then we know the mass of our second cart, which is a little heavier than our first cart, is 0.5 kilograms. The velocity of that second cart initially is going to be 0.5 meters per second, and it's negative because it's in the opposite direction. Then we know the final velocity of just cart 1. And we know at the end it's going minus 1.5 meters per second, so it's ricocheted backwards. And what we're looking for is the velocity 2 final. That's what we don't know. All right, now that we've listed our variables out, we're ready to go ahead and plug them into our equation, and then we'll solve for our velocity final for that second cart. So when we plug in our variables, we're going to put in 0.35 for cart 1 times its velocity, which is 2. And we're going to add that to our mass of the second cart, which is 0.5, times the velocity of our second cart, which is minus 0.5. So that's going to be multiplied. So I'll put that in parentheses there, just so we remember that we're multiplying by a negative number, not subtracting. Now, that's all equal to, not plus, but that's all equal to the mass of our first cart, which is still 0.35, times the velocity of our first cart at the end, which is minus 1.5. Again, I'll put parentheses around that, plus the mass of our second cart, 0.5, times the velocity final of our second cart. And that's what we don't know, the velocity final of our second cart. All right, that's a lot. Let's again start simplifying. And if you want, this might be a good time for you to pause and see if you can finish out the problem. All right, well, let's go ahead and simplify these numbers a bit. 0.35 times 2 gives us 0.7. And then we're going to be subtracting the next term because negative 0.5 times 0.5 gives me a negative 0.25. When we multiply 0.35 times negative 1.5, we get negative 0.525. And that's all going to be plus still our 0.5 velocity 2 final. Now we can combine some of these terms and get 0.45 equals negative 0.525 plus 0.5 velocity 2 final. All right, we're getting there. Now we're going to add 0.525 to both sides. And that'll get rid of that. Okay, so we're adding it to both sides. Just to give us enough space here, I'm going to erase that now, but we're adding it to both sides. And when we do that, we get 0.975 equals, now that 0.525 term is gone, so it's just equal to our 0.5 velocity 2 final. Last step, we'll divide both sides by 0.5. So the 0.5s on the right there will cancel out, and our velocity 2 final is going to be 1.95. Now, we need to round that for sig figs, and it turns out that the numbers we're given in the problem have 2 sig figs for the velocities. So notice velocity 1 initial has 1, 2, and so that's the fewest sig figs. That's what we'll round to, and that will round to the 1 and the 9. Our 5 makes the 9 round up, and we'll get 2.0 meters per second. That's the units there for our final velocity. Let's review what we've learned. We reviewed elastic collisions. We saw those are collisions where things bounce, and that kinetic energy is conserved among several other important properties. Then we developed the equation for elastic collisions step by step. And lastly, we solved 2 different elastic collision problems. Hey, hey.